Hello, ladies and gentlemen. Mr. Dorfler here with your new daily dose of Dorfler. We are on section 5.4, and much to your sadness, this is going to be a short video. I will tell you, though, that you will need at your disposal for today a calculator and a periodic table, okay? So, getting into it so we don't, dilly-dally around here. Yesterday, we talked about a new concept called enthalpy, where we saw that enthalpy and internal energy can be calculated in a very similar, nearly identical fashion, and that since the difference between change in internal energy and the change of enthalpy is really small, it has been allowed to for us to look at the change in enthalpy for changing in energy of reactions. In fact, in order to do that, we have to look at the change of heat. Remember, the change in enthalpy is equal to Q, the change in heat. So, when we look at an idea called enthalpies of reaction, okay, this is where we take a look at reactions and determine how much heat energy is going to either be released to the atmosphere or surroundings, or going to be absorbed. Again, we're going to be using sign convention when we go through enthalpy of reaction to indicate and help us identify if it's an exothermic or endothermic reaction. Okay, so this slide right here has a couple things that we're going to kind of bounce back and forth here. So this states that the change in enthalpy, or our delta H, is the enthalpy of the products minus the enthalpy of the reactants. That little formula right here, okay, right down here, that's going to come into play a little later on in this chapter. Okay, this is just giving us an introduction to this concept. Okay, so eventually we're going to be looking at situations where we need to figure out the complete change of enthalpy when we look at the amount of products and reactants and their change in energy right there. This slide, or this image right here, I'm going to come back to here in just a few moments, okay? But again, this is looking at a diagram to where we have some reactants right here. We have methane and oxygen, and products of the reaction, of the combustion reaction of CO2 and H2O. And in here, it talks about, on the side it says enthalpy is increasing, okay? And the blue arrows indicate what's happening to the enthalpy or the heat of this reaction, okay? And I'm gonna come back to this real quick. So when we call the quantity delta H, it's called the enthalpy of reaction, or other times you're gonna hear it called heat of reaction. Like we see here, we've got hydrogen reacting with oxygen here. And when we have a reaction between hydrogen and oxygen, it forms a completely violent reaction. Some of you may know a really good example of this type of reaction, the Hindenburg reaction. If you don't know what the Hindenburg is, look it up, but it was a very large, impressive blimp, essentially, way back almost 100 years ago or so. And back when they had blimps as modes of transportation, they used hydrogen, which hydrogen is a very reactive gas. And something happened, and it caused the Hindenburg to essentially ignite and catch on fire in a huge ball of flame while it was in the air. It was a pretty bad event. It's a famous saying from somebody watching it was, "Oh, the humanity." So again, that may be something that you heard of. But there are three things about enthalpy that you need to know, okay? First off, enthalpy is an extensive property. We have discussed intensive and extensive properties early on in the school year, but just to refresh your memory, when we say something is an extensive property, what we're saying is it is dependent on the amount of substance that we have that results in the products that we get. For instance, if we had 1 ounce of methane gas, very flammable, Or if we had 10 gallons of methane gas, okay? We have 1 ounce, 10 gallons. If we were to ignite both samples, which would you expect to have a greater amount of heat and energy released to the surroundings? Well, that would be the 10 gallons of methane. So that's what extensive is. The amount you have is going to determine the overall end result. Now, intensive, okay, just to refresh your memory, is those are when we have intensive properties are when we have something that is independent of the amount, like color, okay? If you were to take a strip of loose leaf paper, okay, just take the corner. That color of that loose leaf paper in the corner is going to be the same color as that remaining piece of loose leaf paper, okay? Color doesn't matter how much you have present. It is exactly what it is. So intensive is independent. Extensive is dependent on the amount you have present. So look at number 2 now. Delta H for a reaction in the forward direction. And when we say forward direction, we just mean your typical direction of a reaction. So like we saw in the last slide or two, methane and oxygen react to form CO2 and H2O. That's the forward direction, okay? The usual. Let me just restart this. Delta H for a reaction in the forward direction is equal in size, so the value of this change in enthalpy will remain the same, but opposite in sign to delta H for the reverse reaction. So I'm going to go back here to this. Okay, as you see here, I tried to point at the whatchamacallit, the screen, my computer screen, and it doesn't work for you. So here we have the forward reaction of methane plus oxygen is going to produce CO2 and H2O. In that process, okay, going from these reactants to these products, can you see this blue arrow leading to these products? We have a value of negative 890 kilojoules. Now don't fret, okay? These values are going to be given to you. You don't have to sit there and try to find them or anything like that here, at least not yet. Sometimes we're going to have to use our book, the very back of our book, but not right now, okay? You're going to be given reaction equations, and at the very right-hand side, you're going to have the change in enthalpy value provided, okay? So back to this number 2. So again, going from our methane and oxygen to CO2 and H2O, we have a change in enthalpy of negative 890 kilojoules. Remember that negative sign right here indicates that heat was released. Therefore, it being a negative sign, it is exothermic. But let's just say we reverse, if we can. We can't always reverse it, but theoretically we could reverse anything we needed to fit in our reaction calculations, okay? So let's say we go from CO2 and H2O, they react to form methane and O2. Seems far-fetched, but that's not the point here. So going from these that are now what we consider products, again, this is the reverse direction, they form methane and oxygen. In that process, they have a positive 890 kilojoules. Since it is a positive 890 kilojoules, that means that these reactants here had to absorb 890 kilojoules of heat energy to form these. So we had to kind of break bonds there, reform them. That requires energy. So since it is positive, that means the reverse process will be endothermic. Staying with me here? I hope so. And lastly, number 3, delta H for a reaction depends on the state of the products and the state of the reactants. Okay, number 3 is going to come into play a little bit later on in the chapter when we have to access an appendix in our book in the back, okay, where we have to look up certain values. When we go back to this little equation right here, okay, eventually we're going to get to that and have to calculate it. Not just yet, but we will, okay? When we get to that point, you're going to find that we have substances and elements that can be found in various states, solid, liquid, or gas. And depending on what state they are in, when we are looking at the reaction itself, That's going to determine the amount of energy available from those substances, okay? So we can have water in a couple different ways. We can have it in solid, liquid, and gas. We can have other substances in multiple states of matter. And depending on what the state of matter is, we have different values of energy. So let's look at a practice problem here, okay? This is going to come back to a flowchart-ish type of scenario. You're not really given a flowchart. I'm going to write one down when we get to it, and I want you to write it down too when I give the go-ahead, okay? So our question is, how much heat is released when 4.50 grams of methane gas is burned in a constant pressure system? There it is right there, that constant pressure system. We saw this yesterday. We talked about pressure volume work and the pistons and everything like that, and how we are almost 100% of the time, at least in our classroom, conducting experiments under constant pressure systems. So it finishes by saying, oh, I just threw my marker, that use the information given in equation 5.18. Well, if you look in your book in section 5.4, okay, let me dim this a little bit, okay, this is equation 5.18. It's indicated right here in the brackets, okay? This is the equation that they're talking about. It's also the equation and reaction equation that we've been discussing over the last few slides. It gives us that negative 890 kilojoules value. So that's what we're going to use. So getting back into the problem here, first thing you want to do is write your given. Okay, so this is where I'm going to tell you to, I'm going to actually get back out. Sorry about that. This is where I want you to write down this flow chart. Okay, so first thing you're going to do is you're going to write down your grams, your given. Okay, so this is your flow chart you're going to use for these types of problems. So you're going to have grams of substance. Okay, you will then go to the next step and you'll use the molar mass of substance. 1 second, ladies and gentlemen. I got to find something here real quick. All right, sorry about that, folks. I believe I'm recording now. Anyway, oops. So you're going to use the grams of substance to go to molar mass of substance. Okay. Now, again, I'm just going to kind of put an offshoot here. This is what's going to look like. You're going to have moles over grams. Okay. That's how you're going to set it up. And then finally, you're going to have the delta H value of substance. Okay. And you're going to know that this is going to be written as kilojoules over mole. So eventually, all you're going to be left with is your unit of kilojoules. So let's go over this again. You're going to write down your grams of substance, which will be given to you. You will then have to use your periodic table to determine the molar mass of the substance. Okay, make sure you put it in moles over your mass that you calculate. You will then use the value given to you in the problem or reaction equation, whatever you're given, of delta H value, making sure that it's kilojoules over mole. So let's go back to the practice problem in our notes. So again, we have 4.50 grams of methane. That's listed first. We then have to use methane's molar mass. We get that by looking at the periodic table. We see that carbon is 12 grams per mole, and hydrogen is 1 gram per mole, but there are 4 of them, so 4 plus 12 is equal to 16 grams per mole. Again, making sure moles is on top. And based off of the equation that we saw in the book, because it told us to look there, we put negative 890 kilojoules over 1 mole. We calculate all this out, and we get negative 250 kilojoules of heat that is being released. Again, we know it's being released because we have a negative sign here. Okay. If it were being absorbed, it would be positive, and so would this value. So let's look at our next question here. Okay. Hydrogen peroxide, I'm actually going to take 1 second and just write down the reaction equation. Delta H of negative 196 kilojoules. Okay, so hydrogen peroxide can decompose to water and oxygen by the following reaction, as you see there. And I told you, you were given the enthalpy change right there. Calculate the quantity of heat released when 5 grams of H2O2 decompose at constant pressure. Okay, so getting back down to this. All right, so there's our equation. So again, following that flow chart that I just gave you, the first thing you're going to write down is your mass in grams of your substance. And that is 5.00 grams. Okay? We then multiply by the molar mass, or divide, however you want to say it. If you want to take a time and pause the video to see if you can figure out the molar mass of hydrogen peroxide, by all means. Okay? But I'm going to continue on doing this. If you look at the periodic table, you're going to find out that there are 34 grams of hydrogen peroxide in 1 mole. This allows for the grams to cancel. And lastly, we use the enthalpy value found in the reaction right here. Okay, so we have negative 196 kilojoules per 1 mole. This allows for moles to cancel out. So again, if you want to pause it right here, you may. But after you calculate everything out, you take 5 divided by 34 and multiply by negative 196. You get negative 14.4 kilojoules of heat that is being released. And that is how you do that type of calculation. Okay, nothing too crazy. Again, if you wrote down that flow chart, it's going to help you huge. If you didn't, rewind the video and write it down. It's going to be very handy. But yeah, we're going to be coming and using this type of idea quite a bit throughout the rest of this chapter, okay? We're about halfway through the chapter now, and we're going to be using this concept a bit. So it'll be fun. You'll enjoy it. At least I hope you do. Anyway, that's it for 5.4. Make sure you're staying on top of your problem set, because your 5.1 through 5.3 quiz is just around the corner. And make sure that you have your problem set caught up and ready to turn in on the day of your quiz. Make sure you stay on top of my plan book, because I do update that regularly. And you can see that for any recent updates. Have a good day, everybody.